In today's video, we shall explore how we might implement the retry of CI builds for the Apache NUTX project. What does it mean to retry a CI build? Well, we are seeing problems where downloads will fail during our CI builds, and we wish to retry the builds so that hopefully if we retry it once, twice, maybe 3 times, it will succeed because the downloading has succeeded. Why are we doing this retry? In the last video, we looked at the most expensive PR. This is the PR that took the most amount of time to run during our last 3 months. And we noticed a lot of issues with the downloading of build dependencies during the CI build. For example, if we look at this failure here, we click on it, we can see that this build failed because it tried to download some dependencies, but it failed. If we scroll up to the log here, we can see that it's trying to download DTC, some kind of runtime library. I believe it's for the device tree, and it fails. And this could get quite bad because when we scroll up and look at the other logs, we see that this build has failed a total of 4 downloads. We can see that there's another download for DTC, again, the device tree. And not only that, we see a fail in download for lit metal, which comes from the Open AMP library. This is the open library for asymmetric multiprocessing. This is bad because it fails this particular build. And when the build ends, it fails the entire job with all the other builds, which means that it's a terrible experience for our NUTX developers. Our NUTX developers were to wait close to 1 hour, only to realize that it failed, not because of developers' fault, but because the downloading failed. So this is bad in terms of wasting the productivity of our NUTX developer. It's also very bad for the NUTX project because we have problems with the high utilization of our GitHub runners. We noticed that during the period of January, February 2026 and in December 2025, we had very high usage of GitHub runners. Why is this bad? Well, if we use too many GitHub runners, if our utilization is too high, the ASF infrastructure team will remove our access, will revoke our access to NUTX, to GitHub CI, which means that we will not be able to run any GitHub Actions jobs when that happens. Now, we're not blaming the ASF infrastructure team because this is quite bad on the other Apache projects. GitHub runners are shared across all Apache projects. So therefore, if we consume too many GitHub runners, we are actually depriving other Apache projects of GitHub runners, which means that jobs will just keep waiting forever to run. Therefore, we really have to stay below 25 full-time GitHub runners. This is the acceptable limit. This is way too high. We are trying to address it. And when we looked at the data, we discovered that the most expensive PR was spending a lot of time wasted on downloads that failed. Therefore, one solution is to retry. If a download fails, it should not quit the whole job. We want it to retry. How do we want this to work? For example, if we notice that this particular download failed. Let's go in again. So this is the job for ARM64. Notice that it does a lot of things. It will run, let's go up. It will run a bunch of targets. It will build a lot of targets for that particular ARM64 architecture. You go into PinePhone, VGL, then LCD, and so on. Our proposal is this. If we see that one of the builds has failed, possibly due to a download failure, let's say this build here, let's go down. This build for QEMU, RP server, tried to download the lit metal library, part of OpenAMP, but it failed. What we are trying to accomplish today is that if this build fails for QEMU RP server, it will retry. we will retry this build if it fails, and we hope to retry up to 5 times. And we will put in a random exponential delay between each of the retries. I'll explain that later on. But first, we need to figure out how exactly is this being done? Who calls this script here? And what are the scripts involved? How does this integrate with GitHub Actions? So today, I'll walk through the process of CI builds in NetX, how they're triggered by GitHub Actions, and what we are going to do to change the script so that we can implement retries. And hopefully, with enough retries, we will be able to solve the problem of failed downloads, and our developers will no longer have to wait needlessly for their builds to fail because of downloads failure. And hopefully, we will also solve our problem of the high utilization. Because our downloads are now successful, we waste less time in our GitHub runners executing jobs that we wasted. Now, let's talk about some constraints. So today we'll be talking about doing this. We have for submission of PR, we will want to be able to do builds. We saw earlier on was ARM64, so there are other jobs at ARM01, 02, and so on. Each of these jobs will trigger off smaller jobs. They will build smaller NetX targets. Remember our intention, we want to be able to restart a particular target, a NetX target, if the build fails due to download failure or could be due to some other reason. We have come up with this kind of simplified solution because we are working within a lot of constraints. Let me explain the constraints that we are facing today in the NetX project. We have 3 constraints that I wish to talk about. Hopefully that will help you understand why we came up with this solution. The first constraint that we face is the people. We lack sufficient people to do it. Apache NetX is a fully voluntarily project. It's done by volunteers who are not paid. We are not obliged to do anything for the project. In fact, we could walk away anytime for the sake of our health, for example, and come back to the project when we're ready. So because of the way that the project is structured, we lack enough people to do the whole CI implementation, which means we cannot come up with very complex solutions, and we cannot come up with the people to monitor these solutions when in case any problem happens during the implementation, right? So So in spite of that, we have another problem, which is that everything is mission critical, which means it must not fail. Our solutions, it could be quite complex, but complexity means that it's also quite likely to fail. And we cannot afford the people to monitor it 24/7 to make sure it doesn't fail. CI is mission critical because every time CI fails, it could happen anytime 24/7. The project grinds to a halt. There's no way that anybody could to merge any PRs into the project. This is especially worse during periods where there are a high volume of PRs being submitted, or when we are preparing for NetX release. There's a whole lot of PRs that are being merged, and they need to be successful 100% of the time. The third constraint that we have is that everything is actually very, very complex. We have inherited a very, very complicated build system over the years. It has worked well in its time when we had fewer targets for ARM64, RISC-V and all that. But we are now way beyond that. We've got so many targets, and I don't see any targets being removed. So as we add more and more targets every day, we are having a more and more complex system with all kinds of funny build rules. That becomes a problem, which means that when we implement any kind of new feature into our CI build system, we have to be very careful that it doesn't break some of these complex rules. And the worst part is that some of these rules are so complex that none of us actually understand what the heck is happening inside these complex rules. We don't really know what's happening in there. And because we don't understand what's happening in there, we are very afraid to do something that will break this. So I hope you understand where I'm coming at. These are the constraints that I'm facing today. We have lack of people to do any kind of CI work, and also to monitor the CI when we roll in any changes. Yet our CI is mission critical. Everything must work 24/7. If it fails, we will not be able to merge any PRs. We will not be able to do NATEX releases. But yet we inherited a very, very complex build system. We don't quite understand all of it, and sometimes, if we do the wrong thing, it will just fall apart. So which is why you see my reaction sometimes. Somebody will ask me, why don't we implement this particular feature in CI? It sounds like a great thing that we should do. Well, if you don't hear from me, if I keep silent, if you see me giving the eyes emoji, which are like, rolling eyes and all that, it's because I have these constraints. Firstly, your idea is fantastic, yes, no doubt, but I lack the people to implement it. I don't have people to go through the code, figure out how to do this, implement the code, and then do a 24/7 standby to make sure that this code is really working. It's also a question about mission critical. Yes, your nice new feature is good, but will it break something? Will it cause problems when we have lots of PRs to submit? Will it cause our CI to break during NATEX release? We cannot afford this because NATEX CI is highly mission critical. Then we have this issue about complexity, right? We have so much code in there that we inherited. We're not sure what everything does. If we make some simple tweak, it might break something in one of the legacy builds, and we have no idea how to fix it, right? So forgive me if I hear lots of suggestions, but I cannot implement them, unfortunately, because I have these constraints. These are things that are holding us back from doing any kind of meaningful revamp to our NATEX CI system. So why are we talking about retrying our builds today? Because that seems like it goes against all our constraints. Well, that's because we have the pressure. We have experience from our past PR, our most expensive PR, that things are working out very badly for developers. We have a single build can have 4 download failures, which wastes our developers' time, which wastes our GitHub runners. Therefore, now is the time to fix this. Because if this continues again during the peak period, we will surely have a peak again in our usage of GitHub runners. And unfortunately, the ASF infrastructure team will have to revoke our access to the NATEX CI. It's not their fault. It's really our fault for using too many resources. So that's why we have to think about how we might implement the retry logic, the retry of builds in a way that doesn't require too much development, yet doesn't touch too much of our mission critical processes. And also, we have to be very mindful about the complexity. The scripts are highly complex. We do not wish to touch them too much so that they break. So that's why I'm coming up with a kind of a compromise solution. It's not 100% perfect. It's kind of a compromise, but I think it's the best that we can do within the people and within the time frame that we have right now. So my suggestion is this: we have builds, right? So we have a build that happens. Let's say it's for a specific target, like say QEMU, whatever we saw earlier on. One of the specific targets for NATEX. Today, when this build fails, everything will happily go on with the rest of the builds, and then at the end of the whole build, the whole thing fails, and then causing other jobs in our CI process to fail. So there's a delayed kind of process. There's a delay kind of effect. our suggestion is this: when this build fails, don't report it straight away. We will trigger a rebuild, and this will happen only if it fails. We will redo this, let's say 5 times. We are not sure how effective it will be, but let's put in the code to do this 5 times. It may be that this is excessive, but through our testing, we will be able to find out. Right? So there'll be a retry, retry. And this assuming that everything fails. So at the worst case, if things really fail repeatedly, we will do this 5 times. Actually, there's 4 rebuilds. So we're thinking of maybe putting in one more. Yeah, let's put in one more. Let's put it 6 altogether. So there's 1 original build plus 5 rebuilds. Okay, it sounds a bit excessive, but it's probably easier to implement it now and then take out later. Now, our jobs are running in parallel. We have jobs running, for example, ARM running at the same time as ARM 01 running at the same time as ARM 02 up to ARM 14, then ARM 64, then RISC-V and all that. Everything is running in parallel, which presents a problem. We suspect that some of the download failures could be caused by spamming. The funny thing is that these downloads are coming from GitHub, and yet the download failures are happening even though we are running from within GitHub Actions, which kind of suggests that our parallel builds that we are doing here, they may be firing off too many HTTP requests to GitHub. And GitHub might be thinking that spam is under attack. Maybe it's a DDoS, some kind of attack is happening, and therefore block us. That's one of my hypotheses. Well, through this exercise and through this testing, we'll figure out if that's really the case. So the idea is this: if we build once and it fails due to a download, and we retry again, well, won't we end up re-spamming the same GitHub download, and won't GitHub block us again? Especially if this happens, say, 10 times in parallel. That's why we need to do some kind of an exponential backoff. So, for example, when the first build fails, we will wait 60 seconds. Second build failed, we will wait 120 seconds and 240 seconds. Yeah, you get the thing. So the idea is that we exponentially increase the waiting time for between each rebuild. That's what we mean by exponential backoff. So if something goes wrong, don't retry too soon, because GitHub will probably think that we are spamming it. So therefore, we kind of back off a bit and wait. If it still fails, let's wait longer. So this is 60 seconds here. 120 is twice of 60. 240 is twice of 140, and you get the idea. That's why it's called the exponential backoff. Now, there's also a problem where it's possible that when we do this in parallel, all our parallel jobs will get in lockstep. So that means that the first build fails, let's say for 10 jobs. 60 seconds later, all 10 jobs will reattempt the re-download because of the rebuild 6 seconds, right? And GitHub will think that it's a spam, block us again. And then 120 seconds later, oh yes, the same thing happens again. All 10 jobs will re-download 120, re-download the same thing 120 seconds later. GitHub will see spam, block us again. So that's why we need to do some kind of random factor. So it will be a random number, let's say between 0 to 60 seconds, random. And this, instead of waiting 120 seconds, we do, again, random. 0 to 120 seconds, random. 0 to 240 seconds, random. And so on. So because we introduce this randomness, there is a less chance of our parallel jobs going into lockstep, doing things exactly at the same time. And that will prevent us from triggering too many simultaneous connections to GitHub to download. And hopefully when we do this kind of random exponential backoff, it will prevent GitHub from blocking us. So GitHub will not think that we are trying to spam with too many downloads, and it will allow our download to go through, and everything will succeed. So notice I mentioned that this is a very simple solution. Yes, because we like people to do it. This is the simplest thing that we can do right now. And notice that I'm not even checking whether this build failed because of a download failure or is it because of a build failure. I think for the initial phase, we had to solve the problem quickly. I think this is the best we can do with our limited people and limited time. We have to assume that if something fails, it's highly likely not the fault of the developer, but it's highly likely the fault of our CI system for failing to download things properly. In fact, that's what we see in our last analysis. We see that out of all these things that happened, only one failure was due to a build failure caused by a problem in the code. But we see a lot more other problems due to the download failure. So this is like 4 download failures, 5 downloads failure altogether, versus 1 build failure due to the code. That's why we are quite prepared to do it this way, even though in spite of the reason for failing, whether it's a download fail or whether it's a compiling error, we will still continue to rebuild. We have trust in our developers. We know that they will produce good code, and if they have difficulty building their PRs, we will show them how to build the PRs in their own local repo before submitting to the Apache repo. And in fact, this is a good practice, because then any kind of build errors will be resolved in their own repos, not at the Natex Apache repo, so that the extra time that's wasted when the developer fixes the PR will not be incurred to our Natex project. There. So it's a simple solution. I feel that this is the best way we do right now due to our constraints. Mission critical. Yes, we are just wrapping around a simple function. In a while, we'll go through the function that does this build, and we'll propose to put a wrapper around it, so that we try not to touch too many things. We have a very simple logic. It just terminates after a while. We don't do a lot of funny matching. We don't actually examine the build failure to figure out whether it's a download failure or whether it's a compile error. We will rebuild 5 times, no matter what. The logic is simple. We don't want anything to break in our mission critical Natex CI system. And again, that point about our legacy CI system being super complex, yes, we are just wrapping around the existing CI jobs. We are not really introducing that much anything new. We are not going to touch any of the specific legacy CI builds. We are just simply putting a wrapper around it and introducing rebuilds. Right, we talked a lot about this proposed design. Let's talk about how we might implement this. And to do this, I'll walk through with you some of the Natex CI processes that we are running today in GitHub Actions. How do we get this information? Fortunately, I've written quite a couple of articles. So this is one article that I've written. It's called Preparing a Pull Request for Apache Natex RTOS. Interestingly, I talked about this script here. Now, under this section, we talk about a process whereby developers can run a Docker build on their own machines. How did we figure out these steps? Well, we look at the scripts that were used in our NUTX CI. In GitHub Workflows Build YML, this is the script that will do the builds in NUTX actions. It will trigger off the builds when we submit a PR. When we trace through the script build.yml, we see that it calls ci build.sh. Here is an example of what the call looks like. So this is the expanded version of the script. We're looking at one specific target. We're looking at in fact the the targets for RISC-V number 2. If you look at this file, RISC-V number 2, it will contain a list of targets to build. Like for example, let's say it's for BL602, for Star Pro and Star Pro 64 and so on. The list, the file here contains a list of targets to build. Why don't I just pull it out and show you what it looks like. So if I go to the NUTX repo here, let's open another instance. So let's search for the file. We will look for the file called test this RISC-V. Oh, there. Okay. So I was wrong. RISC-V, the second list of targets, number 2, tells us that within the RISC-V 2 build job, we will build all the ESP32C pseudo-5. So that means it could be C2, C3, C4, and so on. The whole list of test lists is here, and obviously it can be a lot more complex. So for example, in ARM01, we can see that it's going to be a longer list. No, not that long. So it's taking all the ARM32 platforms from A, B to H. Some of them can be quite complex. Like for example, it has CMake in there. Are there more complex ones? There are some rules here. So if you see a minus in front, it means that we are excluding this particular target. So for some reason, this target failed to build. We are excluding it from the NUTX CI. So this build will not be executed as part of ARM03. Yeah. These are the files that will drive the way that we handle builds in NUTX. Let's move back. So when our CI process runs, it will call build.yml, which will expand to a script like this, ci build.sh, passing it the test list file. What happens inside the CI build is that the CI build will call test build.sh, again passing the file here, right? And it will trigger off a Docker run, which will build the job, right? Somewhere in here. Okay, yeah, right. Now, if we are curious about what's inside ci build.sh, just go into this file here, ci build.sh. To be really sure that that's how it works, if you look at the ci build.sh, yes, we can see that it's doing test build.sh when it's provided the list of targets for that build, let's say ARM01. Right? Test build.sh is documented here. In the Apache NUTX jobs, it will look at it talks about test build.sh and how we call it. Right, this is the test list file that we saw earlier on. If you want to see the script, it's here. Now, test build.sh. Remember, we are passing a list of targets in a target list file to this script, test build.sh. Test build.sh will build every single target in the list. It will do a configure, build, run, and refresh. These are the steps it will do for every single target that it sees in the test list target file. Now, but within the test list file, for every single target that we see, it will have this loop. notice that it will look through the targets in the file, it will expand them because of the wildcard matching, and it will call do test. What does do test do? Well, do test is just simply this function here on top we saw earlier on. So it will take one target, it will do a configure, build, run, and refresh. Right. This seems to be the perfect place to do our retry logic. Do tests will return a status. It's called $fail. Unfortunately, it's a global variable. So which means that we need to monitor this global variable to see if the status has changed. If do test was before do test, the status was successful, and after do test, the status is failed. We will need to implement our retry logic. This is the part where we retry 5 times. Remember I said that the $fail is a global variable, so we need to do some kind of masking. We need to implement a local variable instead to capture the status of the fail, so that when we see the local version of fail being set, that means the local do test failing the build, we will do a retry. If all 5 retries fail, then we will set the global flag for failure. Right? This is what we do. We'll do the loop for 5 times. We will do the exponential backoff. That means we will delay 60 seconds, 120 seconds, 240 seconds, and so on. And it has to be randomized. So it has to be a random number between 0 to 60, followed by a random number between 0 to 120 seconds, and a random number between 0 to 240. This seems to be the perfect place to insert the logic. And I think this is our best next course of action. We have to implement the retry logic here, and we have to test it. How will we test it is that we have a NUTX mirror repo. NUTX. NUTX mirror repo is used to run schedule builds. Every 3 hours or so, it will schedule a full build of NUTX, assuming that there are PRs to be that have been committed recently. It will do a full build, and if we implement the retry logic here, this might be a good place to test it, because this thing is running on its own. It isn't really mission critical. Our merging of PRs doesn't depend on it, but yet we're able to see whether our retry logic is working. But how will we monitor the builds here? The good news is that we have today a NUTX dashboard. NUTX dashboard will ingest all the builds from the NUTX mirror repo, like here for example. We will just simply look at this dashboard for errors. So for example, like this is a curl error that's caused by the build job unable to download the ESP32 runtime from GitHub. So these are the errors you look at. For this specific case, it's actually coming from GitLab. That's because we have our own NUTX build farm running on my workstation here, a powerful workstation that will run a whole day, all kinds of NUTX build jobs, and it will record the results in GitLab. That's why we see it in GitLab here. So ideally, we should never ever see any download errors coming from the NUTX mirror repo. Right. There are some errors coming from NUTX mirror repo today, but these are just warnings. It's like it's like failing to connect to a job server. When we click on it, we see that yes, it's just a warning. Everything still goes fine. So I will ignore this, and I will probably change the code so that it will skip these warnings. But we will watch out for any errors coming from a NUTX mirror repo. We will watch out for these kinds of HTTP download errors, whether it's for ESP32, device tree, or OpenAMP, and so on. Therefore, yeah, the NetEx Mirror repo is a good place for us to do this testing, and it'll take a while. It will take a long time to do lots of builds. Remember, we build once every 3.5 hours, so we may not expect to see download errors that quickly, but we will monitor using these logs. Good news is that this thing is automatically monitoring our builds at a NetEx Mirror repo. If we experience any kind of downloading error in a NetEx Mirror repo, then we are pretty sure that our retry logic isn't working. So we are trying to look for no errors in our NetEx Mirror repo to prove that our retry logic is working. So that's our description of the retry logic for our build. Just to recap, we talked earlier on about this code here. So this is test.build.sh. Test.build.sh accepts a list of build targets in the test list file. We will iterate through the targets here to build each one of them. Our proposal is to do this with retry logic. Right now, the function is called doTest. So my suggestion is this. So this is our doTest today. We need to implement this retry logic, right? What I propose to do, build, yes, let's keep it as it is. We'll just rename, we will preserve the name. We will keep the same name, we will call it doTest. That's fine. But then the rest of this, let me see first, is that correct? Yeah, okay. But what about the rest of this with the retry logic? Well, my proposal is that we will simply wrap this into a new function called retry test. So we see that the retry test has got the retry logic. It will simply call doTest, so many times to repeat the test. This, I think, is the simplest way to implement our retry logic without messing up with the complex CI stuff that we inherited. We will simply reuse the existing function for doTest that will do one single build, but we will wrap this whole retry logic into a new function called retry test. So if you can imagine the code here, we will, instead of doing doTest, we will do retry test, and this will also do a retry test. And inside retry test, we will implement this logic to call doTest, and call doTest again for every single retry. And that is our suggestion. So I will have a discussion with our other experts in our NetEx team to figure out if this is okay. This thing is the solution is a bit simple. We are working within our constraints, but there is a danger that it could be a bit too simple, because we are now assuming that every single failure will result in a retry. The failure could be due to a download failure. The failure could be due to a compile failure, which also trigger off a retry. I think that's the best we can do for now, unless maybe sometime in the future we'll do more detailed analysis and figure out what exactly is the cause of the failure. It's not clear when we see through the jobs what failed. So we had to do some very clever pattern matching like I did here. I had to look up all these funny error messages. I have a whole list of these error messages that I match just to find out that it's a download failure. It's something too dangerous to do for a mission critical project right now. We will do with this simple logic. We will test it in our mirror repo. Everything goes well. Let's say after extended period of testing, we might put this into the actual Apache NetEx repo. Now, then there's a lot of discussion also about download failures. Now, doTest will execute a test. Will build a single target. The single target will do its own download. Say downloading the ESP32 runtime, downloading the DTC downtime. Downloading the ESP32 runtime and the DTC runtime. Why not change the logic inside the download? Well, that's a problem because it calls the legacy scripts that we inherited. So remember, the problem is that we have a lot of legacy scripts. These legacy scripts are not downloading things the same way. They are just make files. They are calling curl to download the files. There are many different files that do many different downloads. I don't see an easy way to go in and tamper with every single make file and change all the curl code to do retries, right? This is just too difficult. We will break something. We just don't have the people to do this kind of work. So yes, there's a lot of discussion about can we do retries inside our scripts. My gut feeling right now is just too complex. We have too many ways to download our libraries. One script will be calling curl, maybe something else will be doing some other script, and the curl commands are in different make files. We cannot afford to touch so many make files and make it work. So we talk about other suggestions like, can we pre-download the file before the build? Can we cache the file somewhere during the build? Well, that means that we need to go into all the make scripts and change the curl to read from the cache or to read from a pre-downloaded file, which is a lot of touching of the legacy code, which I really don't want to go there. I see that this is the best way that we can move ahead right now, right? And I would do a revamp of our curl and our downloads and all that, assuming that we can find sufficient people. But today we have a serious problem. We are wasting too much of developers' times on failed downloads. We are wasting too many GitHub runners because the builds fail due to failed downloads. And if we do not address this problem now, we will get cut off from our access for GitHub runners, from GitHub actions. Therefore, it's quite important that we need to test this out today, make sure that it works. It's not perfect, but it could be improved in future. And it could possibly solve this problem of the peaks if it happens again later this year. Right. I just have one more document to share. If you're interested in the way test build works, I have another article that goes into some detail. This article is called Failing a Continuous Integration Test for Apache NetEx RTOS. There is a short description about test build also. So it's quite similar. We see the chain of calls from CI build into test build and all that. And this is specific to CI test, how it runs the CI and all that. So this might be interesting reading for folks who wish to figure out how exactly we are calling our scripts during our CI builds, and especially our CI test. Right, so that's our discussion for today. Hopefully we will implement this soon in our NetEx mirror repo, and we'll get some results to see if this retry logic is working. And hopefully we will prevent a recurrence of this peak problem using too many GitHub runners during the peak period. And of course, hopefully we also hope that we will make our developers, our NetEx developers, a lot happier, so they don't have to wait so much time just to discover that the job failed, not because of their own fault, but because the CI failed to download some dependencies. So this could be a thing of the past. Right. Thank you so much for listening. I'll update you again in the next video.